Hello, everyone, and welcome to our second lecture. I see there's some questions about the slides. Let me see. I thought they're on Canvas. Let me just briefly check that. So they should be available in like 1 minute as soon as this page is updated. Yeah, usually I upload it at around maybe a day before. I don't know. Somehow this hasn't worked this time. Yes, I'm also uploading the tutorial solutions, usually after the last tutorial of the week. Okay, so if yours wasn't the last one, you need to wait until all the students have finished their tutorial. So you should be able to see the slides now. At least when I refresh the page, I can see them. Okay, good. All right, so last time we talked about the ER model, and today we're going to continue there and also going to talk about the relational data model and how we can map the ER model to the relational data model. Okay, so first let's start by revisiting some of the concepts that we discussed. You're probably already familiar with this meanwhile, because most of you have attended the tutorial. So the main concepts that we're looking at in the ER model are entities, and we distinguish between entities, entity types, and entity sets. Okay, so we have these three different ways to look at the same thing. So an entity type is basically a description of the entity with a specific, so it tells us what kind of attributes the entity has and the names of these attributes. Whereas an entity set, you can think of as like the state of your database regarding that entity, right? So all the instances of that entity that are currently in your database, those will be in the entity set. And of course, entities have attributes. So I won't go into too much detail here. And just to keep in mind that attributes usually have a domain associated with them, right? So for example, if you look at the name attribute, then it usually will be some character string, or an ID could be an integer, and so on. So there's another question in the chat. So can we have the tutorial answer as well after today's class? Yeah, so as I said, so I'm going to upload that. So all the tutorials are now complete. So I will upload the tutorial solutions right after the lecture. Okay, and yeah, some of you sent me a question about the course content yesterday. I didn't have a chance yet to reply, so don't worry, I will reply. I just didn't get around to it, so I'll do so later on today. Okay, and we can have different attribute types. So an attribute can be simple or atomic, meaning it's just some value, or it could be a composite attribute that consists of multiple simple or also composite attributes. We also talked about multi-valued attributes, meaning an entity can have multiple values for that same attribute. So for instance, when you look at that company database, then we saw that a company can, or rather a department can have multiple locations. And finally, we also discussed derived attributes, which are those that you can derive from the data that is already in the database, right? So for instance, age could be a derived attribute if you also store the birth date. And finally, the third piece in the ER model are relationships. And a relationship is just an association among several entities. Okay, so we saw many examples for this also in the tutorial. So here's the works on relationship. And again, similarly as for entities, we distinguish between relationship, relationship type, and relationship set. All right, and we can have some constraints on the relationships in our ER model. So one such constraint is the cardinality ratio. So that specifies when you have a binary relationship, whether that is a one-to-one relationship, a one-to-n relationship, or an n-to-n, meaning a many-to-many relationship. Okay, and down here, you can see two entity types, A and B. And you can imagine these green dots here to be your elements in your entity set for A, and these green dots here are the ones for B. And the lines between these dots here are basically the relationships. Okay, so you can see that for many-to-many, we have some arbitrary lines here. So there's no restriction on the degree of any of these green dots. So if you just think of this as a graph, then of course, if you have, for instance, a one-to-one relationship, then each vertex in your graph can only have a degree at most. Well, so there are two ways to indicate the cardinality ratio in an ER diagram. So one is the way that we already seen last time and also in the tutorial, namely you just write the appropriate number on the link, right? So a one-to-one relationship, I would just write the one here and the one here, and similarly for one-to-n and m-to-n. But you could also use this notation, which is also commonly in use, where you just place an arrow on the one side of the relationship. Right, so meaning if it's a one-to-one relationship, then you have arrows on both sides, and of course, if it's a many-to-many relationship, then you don't have any arrows at all. So we also discussed these participation constraints, right? So sometimes we want to make sure that each entity must participate in the relationship. So for instance, when you, again, coming back to the company database, so we had this restriction that each department is managed by someone. Okay, and therefore we use this double line here to emphasize this. Okay, so this becomes a total participation because we want each department to be managed by some employee. All right, so now here's an alternative notation that you can use to specify some structural constraints. So this is this min-max notation. Okay, so you specify the minimum and the maximum number of relationships that an entity can participate in. But this notation is specified for on each participation of an entity type E in a relationship type R. Okay, and as I said, it specifies that each entity E will participate at least a min number of times and at most a max number of times in the relationship. Of course, the default is that you don't have a constraint, right? So that min is 0 and max is n, where n stands for some arbitrary integer. And of course, it doesn't make sense to have, for example, a minimum that is larger than the maximum, and also these obvious constraints need to be satisfied. Okay, so in the company database, we would use this notation to specify the constraint that exactly one employee is the manager of a department, and an employee can manage at most one department. So we would write a 0, 1 for participation of employee in the manager's relationship, and a 1 to 1 for participation of the department in the manager's relationship. Okay, any questions so far? Good. All right, so now similarly for 1 to n, I think this is so basically. So actually, let me just show you the picture here, right? So maybe this makes it clearer. Okay, so an employee might manage 0 or 1 departments, but each department is managed exactly by one employee. All right, so this is a 1-to-1 relationship where we also, so this min-max notation here not only allows you to specify the cardinalities, but also the constraints on the participation. Okay, because this is a total participation constraint here, we have the range restricted exactly to 1. Whereas on this side here, employee has a partial participation constraint, so it may or may not participate in this manager's relationship. So that's why we have either 0 or 1. Okay, and so here we have the 1 to n relationship, right? So again, in this notation, what we get is the following. So on the employee side, we have a 1-to-1 constraint, right? Because an employee works for exactly one department, and it's a total participation, right? And on this side here, we have a 1 to n constraint because a department, so basically because any number of employees, or rather at least one employee works for a department, but any number of employees can work for a department. Okay, and this is the picture that we had last time for the company database. And now just to show you how this looks in the different notation, here's the picture for that. And now let me run a short poll. All right, so, okay, so most of you. Okay, so let me share this with you. All right, so most of you have the right answer. Okay, so it becomes a strong entity. So yeah, okay. Yeah, it seems a bit strange how exactly Zoom is calculating this, but yeah, there's some rounding errors, I suppose, in the percentages. And let me just check. There was a question in the chat. So the double line for dependent, so you still need that around the diamond, right? Because you want to emphasize that this is the identifying relationship. Okay, but strictly speaking, you're right that we don't really need this, this double line anymore, because you're already specifying this total participation using the one-to-one constraint. Okay. But on the other hand, nobody stops you from still adding these double lines if you like. So it really depends on how formal you want to be. Okay, any other questions at this point? Good. All right, then let's move on. So the degree of a relationship type is the number of participating entity sets. And so far, we only dealt with binary relationships. Sorry, I missed one question in the chat. So how come supervisors can have no supervisees? Yeah, I guess it depends on how strictly you want to modify that. Someone could still be a supervisor if it doesn't have any supervisees, right? But of course, maybe it is a restriction, then you want to also specify total participation for that. Okay, so the relationship, so the degree of a relationship tells us how many entities will be in one of these in the relationship. Okay, so it could be that that more than one relationship type exists with the same participating entity types, right? So it's not necessary that if you only have entities A and B, that they're exactly in one relationship to each other. And in fact, we saw an example for this on the previous slide, right? So we have multiple relationships between employee and department. So now let's look at relationships that have a higher degree than binary, because you might already have seen binary ones sufficiently often. So usually you don't see any higher degrees except maybe degree 3 in the real world. So let's just focus on ternary relationship types. In principle, the ones that encompass n different entities are called n-ary. So let's look at this example where we have a supplier A that supplies a part for some project. Okay, so now you have 3 different entities, right? You have the supplier, you have the part, and you have the project. And they could be in a ternary relationship that is called supplies. Okay, so now in general, we can't just say that an n-ary relationship can be replaced by n-binary relationships. That's unfortunately not how it works. So there's a question in the chat. So 3 objects have relationship with each other, then yeah, we're gonna see some examples for that in a second. And that will be become 0. But one downside is that if you have these higher order relationships, then it becomes harder to specify the constraints that you have. Okay, so that's why most of the time people are doing their best to just have binary relationships. Okay, so here's the example. Here's the picture for the example where we have a supplier entity and a part entity and also a project entity. I should say entity type for these three. And you can see the corresponding entity sets here. So these are the elements of the corresponding entity sets. And here in the middle, we have this ternary relationship called supply. Okay, so it's ternary because each one of these elements here concerns these three relationships. Okay, so now let's look at constraints on higher order entities. So in general, what does it mean if we have these entity constraints here? Or I should say the cardinality constraints. So in general, it means that the cardinality of each entity type in a relationship is the number of distinct values for that entity type that can be associated with each valid combination of the other entity types. Okay, so this is exactly what we get in the binary case too, if you think about it, right? But let's look at some examples. Okay, so let's not worry too much about what M, N, and L actually means, but let's look at some concrete examples here. So here we have, let's say that the following setting. So let's suppose that for each project PJ1 and each part P1, there's at most one supplier S1. Okay. So basically, this means that I can have a relationship PJ1, T1, and S1, but I can't have another relationship in my relationship set that says PJ1, P1, and S2, where S2 is a different supplier. Okay, that's not possible according to this requirement here. So what does this tell me? Okay, so I'm basically fixing two of the three parts here. So I'm looking at a project P1 and at a part P1. Okay, so I'm fixing these two entities here. And now I'm trying to determine how many suppliers can I combine with these two fixed entities. And the answer is 1, right? Because that's our requirements. There's at most one supplier as 1. So I should write a 1 up here on the cardinality constraint. Okay. So there's a question in chat if there's a unique supplier. Now, we didn't specify any, so assuming, let's not worry about participation constraints now, so you can think of it as a unique supplier. Okay. No, there can't be a lot of suppliers for the same project and the same part, right? Because I just said that if you fix the project to be some fixed project PJ1 and some specific part P1, then I can't have like another supplier S2. Okay, so that's why here we have this 1 up here. Okay, so this is the first constraint. And this is actually nothing different than what we did in the binary case, right? Because the only difference was that we didn't have to fix two entities. We just had to fix one entity. Okay, clear so far? So let's look at the second requirement that we have, so that we can determine the other cardinalities here. So let's also assume that a supplier S1 can provide the same part PJ1 to multiple projects. So now we're fixing the supplier and the part. Okay, we fixed S1 and we fixed PJ1, and we are trying to understand. Sorry, this should be P1, not PJ1. Okay, so we fixed S1 and we fixed P1, and we're trying to understand how many distinct values for project can we have. So, and the assumption here tells us that we can have many, right? So now, therefore, we should add a cardinality constraint of M here, okay? Meaning basically we don't have a cardinality constraint. All right, so, and again, looking at the kind of tuples that we can have, just erase this, what I wrote over here. So basically this tells me that I can have some project PJ1 and some part P1 and supplier S1. And I could also have another relationship project PJ2 with the same parts and the same supplier. Okay, so all right, so now we fixed part and supplier. So this was the second cardinality that we determined, and now let's look at the third one. So we want to determine this cardinality here. So we're going to fix supplier and project. So now we're looking at this assumption. So for each supplier S1 and each project P1, multiple parts may be supplied by S1. Okay, so each supplier may supply multiple parts for the same project, and therefore this will be an N here. Okay, so this is how we can determine the cardinalities of a ternary relationship. But of course, it really depends on the assumptions that you're making, right? So if I don't give you these assumptions down here, then you have no idea what to write here. It could be anything. I'm sure you can change M and N. So as I said, it doesn't matter whether you write M up there or N down there. It just means that this is an arbitrary integer. Okay. All right. Good. So here again, we have this example relationship, this ternary relationship, and now we also make it more interesting by adding some more attributes here. Okay, so we add a quantity to our supply relationship, which tells us how many, or rather what quantity of a specific part is supplied by a specific supplier to a specific project. Okay. Now, the reason why we can't just replace this ternary relationship by 3 binary relationships is the following. Let's say we try to do that. So now you get something that means something different, right? Oh, okay. So again, when I exported this this slide to PDF, I guess PowerPoint did not remove these boxes. All right, I'll check that out later. But thanks for letting me know. Okay, so now we have 3 binary relationships, right? So we have one between supplier and project, one between supplier and part, and one between part and project. And to make this, well, that's just an assumption. Okay, so let's not worry about it here. You're right that in the real world, if this was a real database, then you probably want to have something else at the key and not just the supplier name. Okay, so now if I have like, let's say in this ER model here in part B, let's say I have 3 relationships, S1 to P1, S1 to PJ1, and P1 to Pj1. Now, this is not exactly the same as having this triple here. Okay, because it just tells us that this supplier S1 can supply some part P1, but there's nothing said here about the project, right? So this is just some relationship between supplier and part. And this only tells us that this supplier S1 is a supplier for that project P1, Pj1. And similarly, this here tells us that the part P1 is used in the project Pj1. But these three things here do not imply that now this relationship holds, right? This ternary relationship. Okay, so you can think about this and probably you can come up with some counterexamples. Now, there is a way to simplify these ternary relationships, and that is by introducing a weak entity instead. So I can make this ternary relationship supply, the one up here, I can make that a weak entity with the same name, and it also has the same attributes. And now the difference is that I have three identifying relationships, okay, so namely to all the entities that were in this relationship up here, okay. So there's a question. So when they're all linked by one relation, then the degree is 3. Yeah, so the degree is the number of participating entities in a relationship. Okay. So the names of these relationships relationship types down here, SS, SP, and SPJ. So these are just, I have to give them some names. So I'm just gonna use the first letter of this entity and the first letter of this entity and so on. So I just use some abbreviation for this. So SS stands for supplier supply, and SPJ stands for supply and project, and SP stands for supply and part. Okay. So so there's another question. So the degree for C is 2. So yeah, so down here we only have binary relationships, right? So each one of these diamonds here is only connected to 2 entities. So the degree is 2. And as I said before, so these are the most common ones, right? This degree 2 entities. Now, another way to get rid of the ternary relationship is to actually add an artificial attribute to your supply relationship. So you could, for instance, add a supply ID as a key and even make it a strong entity. Okay, and then you don't have these identifying relationships, you just have normal relationships. Okay, so let's move on. So now we're done with the ER design. So you should have some understanding how to come up with these ER diagrams, I hope. So now we can talk about the relational model and how to get a relational schema from an ER model. So even though the ER approach is quite simple and also gives you a nice intuitive way to describe the structure of your data, most database implementations are based on the so-called relational model. And that's why we need to talk about how to transform our ER diagram to this relational model. Now, the relational model itself was first proposed by Codd, who worked at IBM Research in the 70s, in the following paper here. And this paper has been cited many thousands of times. And in fact, it was a major revolution of the field of database management. And this was probably one of the reasons why Codd received the ACM Turing Award. So if you've never heard of the Turing Award, you can just think of it as the Nobel laureate for computer scientists. Okay, so let's start with an informal description of the relational model. So the relational model just represents a database as a collection of relations. And a relation contains a set, looks like a table, Okay, so you have some number of rows and some number of columns, and each one of these cells in your table will be some value. Okay, so on an intuitive level, you can think of a relation as like a table in an Excel sheet. Okay, so someone already wrote in the chat like no Excel. So yeah, you can think of it in that way, but as we saw in the tutorial, Excel sheets don't give you the same guarantees as databases. Okay, so a relation contains a set of rows, which are usually called tuples in the context of the relational model. And the data elements in each such tuple represent certain facts about real-world entities or relationships. Now, the columns that we have in our relation, so each one of them has a column header, and this header will tell us something about the meaning of the data items in that column. Okay, so basically each column corresponds to an attribute of that relation. And of course, each attribute will have some set of allowed values, which represent its domain. Okay, so here's an example for a relation. So the relation is called movies, and we have 3 attributes: title, year, and length. And we also specify the domain in this type notation here. So title as a domain string, year as a domain integer, and so does length. Now, when talking about domains, keep in mind that it's not necessarily the same as these simple data types here. So you could have more restrictive domains. For instance, the domain of some attribute might be all valid Hong Kong phone numbers. Okay, so then it's not just the set of all integers, because there's some additional structure imposed on that. So here's an example of a relation. And you can see here that we have the tuples. Each tuple corresponds to 1 row in our table here. And at the top here, we have the relation name, and the columns are given by the attributes. Now, again, we would use this notation here. So usually it's common to write the name of the relation in capitals. So this is just a common usage. Nobody's going to complain if you don't do that. So there's a question: can you have double domain? So I'm not sure what you mean by double domain. In case you would like to clarify. Okay, so I guess some of you are getting excited about the fictional GPA scores here. So let's move on. Let's talk more about the values in a tuple. So all values that we consider here are atomic, meaning they're indivisible. So we don't have these composable attributes that we had when talking about the ER model. Okay. And the reason for that is simple. So I want to be able to directly manipulate such a value. So I can't easily do that if we had composite values. So of course, each value that is in the same column needs to be from the same domain, meaning the same set of allowable values for the attributes in that column. And we also have a special null value that represents all values that are either unknown at the moment, not available, or inapplicable for a specific tuple. Okay, so again, looking at an example here. So now here we have this column office phone, and you can see that some of the tuples here have a null value as the entry. Okay, and that just means that we don't know the office phone number, or that student doesn't have one. Now we use the following notation to talk about specific values of a tuple. So we either use this so-called array notation, right? So when I have a tuple T, and in these brackets here, write AI, then this will give me the value of the attribute AI for tuple T. And sometimes you also see this notation, this dot notation here. Okay, so this is T dot AI again refers to the same thing. It will give me the value of attribute AI for tuple T. Now, each relation will have many records or tuples in your database, right? So just to let you know, so sometimes we call tuples also records, and the reason for that is that they usually refer to records in files, but that's more about the low-level organization of databases, which we'll discuss later on. So at any point in time, you have some specific relation state, which corresponds to all the data that you currently have in your relation. So if you just look at the collection of your tables, then you just, that will give you your current state. And of course, as soon as the database is updated, a new state arises. So there are basically three operations that you can have for changing the database: insert, delete, and update, which is also sometimes called modify. As the name says, insert will insert a new tuple into a relation. Not by coincidence, this is the same name as is used in SQL. Now, delete, as the name says, will remove an existing tuple from a relation, and update will update a specific attribute for an existing tuple. Okay. All right. Any questions so far? So here's an example for the populated database or your relation state of the company database. Okay, so we haven't really discussed how we get these specific tables here for the company database, right? We only designed the ER model for this database, but you could think of this as a snapshot so far. And here's a summary that tells you how these informal terms that we're using all the time correspond to the formal terms, right? So the most common one is that people just talk about tables when in fact they mean relations in the relational model. So there's a question: can a data domain be a double domain? I'm not sure what you mean by that. So do you mean that a domain can occur twice in the sense that two attributes can have the same domain? Or do you mean that one attribute can have two domains? I see. So, okay. So then, if it's a string plus an integer, so yeah, it's still, you would just treat it as a string. But in general, if you really have like multiple attributes, or rather multiple domains for a single attribute, then you will just define your domain to be that. Okay, so a domain is always one thing. All right. So maybe I could have an attribute that is either, let's say, a Boolean or an address. I don't know why anyone would want that, but it's possible. So then my domain would be that, well, it's a string or it's a Boolean. Okay, so one of the two, but it's still only one domain. Okay, good. Any other questions at this point? What is the last two rows on the slides? Not sure what you mean by that. So there's a question: why is student a relation name? Yeah, so we'll come to how we map entities to relations. We'll talk about that in the next hour. So here what I did was I just write the relation name on top of the relation table. Okay, so basically the state here is just shown underneath the corresponding relation name. Okay, and just to, as you can see here, we already underline the attributes that correspond to keys. So for instance, this social security number for employee, we determined last time that that is a key. So I'm also underlining that here. All right, so again, what does it mean to be a key? Well, you won't find any two entries in your table here that have the same value in this column. Okay. All right, so let's continue maybe in 9 minutes at 5 o'clock. All right, so let's continue. And I see there was a question in the chat. So one question was the relationship is only the user's definition. So I guess this refers to the question here. So can you explain what the table definition and populated table? So the difference is that the table definition just tells us what kind of attributes a relation has and their domains, right? So it doesn't tell us anything about the actual values that are in that table. Whereas the populated table, the one that we are seeing here, so that contains, that basically displays our actual values in the database. All right. Good. Let's continue now. So one point about the ordering of these tuples here. So usually when we have a table, then you have the first row of the table and the second row and so on, right? So there is an ordering. And that ordering is also something you can make use of, for example, in Excel. But the point is that tuples are sets, or rather they are in these sets, right? So a relation is just a set of tuples. And so they're not really ordered because a set is not an ordered collection of elements. It just contains these elements. There's no ordering there. So that's why usually we don't assume that there's some ordering on the rows in such a table. Now, on the other hand, when we look at the attributes of a specific relation, and sometimes you call this relation schema, right? So if we have our relation R, then we do care about the ordering. Okay, so usually we will describe a relation R in the following form. So we have R, and then we have all the attributes of R, A1, A2, all the way to AN. So tabular form means that it's in this, form like a table, like an Excel table. Okay, so of course this, this description, this relation schema is ordered, and also the values are ordered, right? So you can't just swap the values from column 1 with column 3 and expect it to be the same. Okay. So the takeaway from this slide should be that there's no ordering on the rows, but there is an ordering on the columns. Okay, so here's an example for that. So here you can see actually that these two tables represent the same relation state. The only difference is that I reordered some of the tuples. All right. Okay, so now let's finally talk about how we can actually get a relational schema from a given ER model. So the high level idea is that we're going to turn each entity set into a relation with the same set of attributes. So this is, take these two things here with a grain of salt. So this is just a high level idea. Okay, so you'll see that we need to be more careful when we do this. And also we're going to replace the relationship by a relation, or rather just attributes of the connected entity set. Okay, so this means that when I have a relationship in my ER diagram, I might just make that relationship, I might just model that relationship as a set of attributes of one of the participating entities, or I might create a separate relation, meaning a separate table for that relationship. And I hope that doesn't confuse you, but there is a difference between relation and relationship, right? So relationship is what we have in the ER model, whereas relation is what we're looking at in the relational model. Okay, so again, we're going to look at this company database. So we will map this ER model here to a relational model. And this will be the result of our mapping algorithm. So now let's talk about how we actually get this. And I will also explain, of course, what all these arrows here mean later on. Okay, so let's define that ER to relational mapping algorithm that makes this work. So we're using the company database as a running example, and our algorithm will create tables or relations, right? The same thing. with simple single valued attributes. So the first step that we do here is we map the regular entities that we have, entity types, in the following way. So for each entity type E, we create a relation E. Okay, and we include all the simple attributes of that entity. So for each attribute that we have in our ER model, we're just going to add a column. And if we have composite attributes, we're going to just also include the components of the composite attributes. Okay, so I'm not going to, so for instance, if I have a composite attribute that is called name in my ER model, okay, and this is connected to some entity here, let's say person. This composite attribute consists of first name and last name. Then what I'm going to include in my relation is the following. So I'm going to create a relation called person, and I will include F name and L name, okay, but not name itself. And what do we do with the keys? Well, we choose one of the key attributes E as the primary key for our new relation. As I mentioned, we might have multiple key values, key attributes, sorry, in the R model for an entity, but we only can choose one as the primary key, and we're going to underline that one in our relational model. Now, these relations that we get from this step one process, these are called entity relations because they correspond to entities in our AR model. And of course, each tuple that we get will represent a specific instance of an entity. Now it could be, so just one more word about mapping these key attributes. So it could be that you have multiple keys, as I said, right? So if multiple keys were identified for your entity E during the conceptual ER design, then the information describing the attributes that form each additional key, that is kept. The reason for that is that we might need some secondary keys for a relation that can be used for indexing purposes. We'll talk about indexing in a few weeks' time. Okay, so here we can see a picture of what is going on in step one. Okay, so we have our entity over here, and it has attributes A1 to AK, and A1 is a key attribute. And we have this entity set, which consists of E1, E2 to EJ. So then what we get here is this table or this relation E with all the simple attributes A1 to AK, and as the column headers, right? And then the rows are the elements of our entity set. Okay, so I will have J rows here. All right, so I hope so far this algorithm is not too difficult. So what kind of relations do I get as a first step from the company database? Can someone help me with that? None at all? I don't get any relations? Well, what do we do in the first step? We're mapping all the regular strong entity types. Okay, so what are the entity types here? Well, we have employee, department, project, right? So these are the three that we get. Okay, good. All right, so this is what we get here. So I'm underlining the primary key, social security number for employee, department number for department, and project number for project. And I'm including all the simple attributes. And this was a composite attribute, so I split it up and I just include its components. All right, so now this brings us to the step 2. Now we need to also map the weak entity types that we have identified. So for each weak entity type, we're going to create a relation with the same name. So for each weak entity type E, we have a relation E. And again, we're going to include all the simple attributes and all the simple components of composite attributes. So far, it's almost the same as for strong entity types. And now I also need to include the primary key attribute of the owner identity, which is the one to which this weak entity is connected using the identifying relationship, as a foreign key attribute. Okay, so if you think back to how this works between employee and dependent, right? So what would we include for the relation that we create for the weak entity dependent here? What would be our foreign key? Well, it would be the social security number, which is the primary key of the owner identity, which is employee. Okay. All right. So, and then the primary key of this relation is the combination of that foreign key that I had to include, and also any partial keys that I might have in my weak entity type. So again, thinking back to dependent, dependent doesn't have any, I mean, dependent has a partial key dependent name, right? So then the primary key would be the employee's social security number and dependent name. Okay, so here we have again a picture that shows how this second step works. So we have a strong entity here on the left, which owns this weak entity here, EW. Okay, so these are connected in a 1-to-n relationship. And you can see that W1 is a partial key for EW. So down here now, we have all the attributes of EW, which is W1 to WN. And we also add S1 as our foreign key, which is the primary key of this relationship that we have identified in step 1 for this strong entity here. Okay, so we will come to that, to these multi-valued attributes. Okay, so that will be a later step. So for now, we only talk about simple attributes. Yeah, in a sense, you can think of a foreign key as kind of like a reference to some other entity, okay, to the key of some other entity. So obviously, any value here in this column, so let's say you have value 34 here. So you can only have a tuple in here with this foreign key 34 if there exists actually some entry over here with 34, for instance, right? Okay, so so you can't like have values that don't exist over here. So you can't have foreign keys that aren't represented in the entity to which they're referring. So there's a question. So yeah, S1 was the key here from this strong entity, right? So that's why we're including S1. And the second question was 2 underline means weak. And so actually we don't have any double underlines here, right? And so we map the primary key from the strong plus the weak entity key. So yeah, so we use the primary key of the identifying entity, which is ES in this case, and we use that as a foreign key. Okay, so S1 here is a foreign key. And this dotted thing here, that is a partial key. That's the ER notation that we have for that. All right. Good. Okay, so after step 2, we get another relation here. All right, so we get the dependent relation, which we get for the weak entity dependent. And now you can see that we underline both the employee social security number and the dependent name. So both of these together will form our primary key for dependent. And we emphasize that this is a foreign key. So we use this arrow notation here. So we just point from this attribute here to the place, to the place from which this is the foreign key of, right? So this is the foreign key of this primary key here of employee. Okay, so we just make sure that we know where this foreign key is coming from. There's another question. Do we have an extra symbol for weak in relational model? So, there's no longer any notion of weak or strong here. We only have some collection of relations. Okay, so this is the relation, and it's it's a relation that has a foreign key, but otherwise you can't distinguish it from any one of these other relations here. Okay, so there's no longer any distinction in the relational model. That's only in the ER model. All right, so now let's move on to step 3. So now we're going to map the binary one-to-one relationship types. Okay, so let's do that. So for each binary one-to-one relationship type R that we have in our ER model, we're going to identify the relations that correspond to the entity types participating in R, right? So R will just be, something like this. And here I have two entities connected to it, E1 and E2. And I see there's another question. So yeah, so let me just go back to that. So one of you asked why this is called ESSN, right? So in principle, I could just also call this the same. Sometimes people rename it, but that's strictly speaking not necessary. Okay. So if you like, you can even use the same name for both. Sometimes this is actually useful, so it makes it clearer where this foreign key is from. And there's a question why this is underlined. Well, I need this key from this identifying relation up here, the one that I had from this, this is what I mapped to my strong entity from the ER model. So this key here is used here as a key in my weak entity that I had in the ER model, right? So now in the relational model, I also need to underline this to make it together with the partial key dependent name to make these jointly primary key. Yes, so ESSN and dependent name, that is a key for dependent. Yes, that is the primary key here. Okay, so coming back to how we map these binary one-to-one relationships. So there are 3 possible approaches: the foreign key approach, the merged relationship approach, and the cross-reference or relationship relation approach. Let's discuss each one of these separately, but just to keep in mind that usually you will probably want to use the foreign key approach unless there's some other constraints that stops you from doing that if you have a one-to-one relationship. Okay, so let's start with the foreign key approach. So we have some relationship between S and T, and we're going to just choose one of the 2 relations. And note that these were entities in our ER model, right? But now they are relations because I already mapped them in the first step. Okay, so now I'm looking at the relations in my relational model. So I'm just gonna pick one of the 2. So let's say I pick S, and I will include the primary key of T as a foreign key in S. Okay. Also, I will include all the simple attributes of the relationship in S. All right, so this is also not too difficult, I hope. Now it's better to choose, the entity type that has a total participation, if there's one, in the role of this entity of this relation S of here. Okay, so so what do I mean by that? So why do I want to choose the one that has total participation? Right, so I want to avoid having null values. Okay, so if I don't have a total participation, if I only have partial participation, so then I will have some, I might have some tuples in my relation S where the foreign key has a null value, simply because that specific entity instance does not participate in the relation with T. Okay. Now the second approach here is to use the merged relationship approach. So I can do this when both relationships have a total participation ship. So then what I can do is I can just merge the two into a single relation. Okay. The reason why I can do that is because both of them will have exactly the same number of tuples. And finally, there's the cross-reference approach. So in that case, I will just set up a third relation R to cross-reference the primary keys of S and T. Okay, so this is kind of the most general approach, right? And we'll see that this approach works for any cardinality of relationships when I map them, not just for one-to-one relationships. Now, about this third relation that I'm creating here when I do this cross-reference. So of course, I need to include the primary key attributes of S and T as the foreign keys to S and T. Okay, and just to make it clearer what I'm talking about here, so I have S, I have R, and I have T here. Right, so and now I just, in this third approach, this cross-reference approach, I just made R its own relation. Okay, and I will need to include the foreign keys of S and also of T. Sorry, the primary keys of S and also of T as foreign keys here. Now, since I have a new relation R, so what's the primary key of this relation R? Well, it will be one of the two foreign keys. Okay, so why not both? Why don't I choose both of them as my, or maybe I need to choose both of them as my primary key? Why is it sufficient to choose, either the one of S or the one of T? Well, the reason is actually because this is a one-to-one relationship. Okay, so I don't need to include both keys. It's sufficient to include just one of them. Okay, it can't happen that let's say some entity of entity type S is in a relationship with more than one entity of entity type T, simply because I have a one-to-one relationship. Okay, so that's why one is sufficient. Okay, oops, I didn't want to zoom here. All right, so now in this, after this third step here, so what do we do here? Well, here we map the one-to-one relationship managers. Okay, so if you remember in our company database, we have this relationship between department and employee. So each department is managed by one employee, and each employee manages one department at most. So therefore, now what we do here is we take the department the department relation that we previously mapped. And now we add the primary key of the other relation, namely employee, as a foreign key. Okay, and we rename this as manager social security number, just to make it clearer what this is referring to. So there's a question. So I'm not sure I understand the question. So originally, both S and T have a primary key R, and R is total participation. Yeah, I'm not fully following what you mean by that. Maybe you want to rephrase it while I continue here. Any questions about this slide here? So is it clear why we added this, this foreign key here? Okay, so this foreign key. So I just mapped this this manager's relationship from our ER model to the relational model by adding this foreign key here to department. Okay, so let's move on to step 4. So now we're going to map the binary 1 to n relationship types. Okay, so how do we do that? Well, we're going to use the foreign key approach. Or rather, there are two approaches, but the first one is foreign key. So we're going to identify the relation T that represents the participating entity type at the n side of the relation. Okay, so again, we have this picture here where we have S, and we have some 1 to n relationship. And here we have T. And T is the one that is on the n side. There's a question in the chat. So any order requirements to add the key? So no, in principle, you can add the key anywhere in the order of attributes. Doesn't really matter. And also another question. So manager social security number is a foreign key from employee. Yes, that's right. Okay, so I'm going to identify this entity here that is on the n side. And then I'm going to include the primary key of the other entity type, namely S, as a foreign key in T. Okay, and intuitively this makes sense because you know that each entity of type T will be in this relationship with at most one entity of type S. Okay, so you either have a foreign key or you have a null value in that corresponding key. And we're also going to include the simple attributes of this 1 to n relationship type as attributes of T. So what do I mean by that? Well, here this relationship might have some attributes, maybe an attribute A1 and so on. So I will just add these attributes as attributes in my relation T. Now, alternatively, if you don't like this foreign key approach, then you can do the cross-reference approach. So this works exactly in the same way as we described it for binary 1 to 1 relationships. Okay, so you create a new relation for this relationship here, and then you add the primary keys for these two as foreign keys. Okay, so let's look at what we get if we do this for the company database. So now we have the relations supervision, works for, and controls. Okay. So here you can see what we get for adding this supervision, for mapping this supervision relationship. So if you remember, supervision was a recursive relationship. So it was between employee all right. And this was a 1 to n relationship. So it doesn't matter if it's a recursive relationship, we do exactly the same thing, right? So employee is the same entity that we're looking at on both sides of the relationship. So we take our relation that we got for employee, and now we add this foreign key, which will now be the the primary key of employee. So we will just add a super SSN attribute, which now refers to the supervisor social security number. Okay, and again, to emphasize that this is a foreign key, we add this arrow here to the actual primary key, which we're referring to. Now, this arrow here, or rather this field here, so this is the department number. So this is added as a foreign key to employee. So this points to department number down here. And the reason for that is that each employee works for one department. Okay, so employee is on the end side of the relationship. So that's why we're adding this field here to employee. And similarly for this relationship here, so here we added a field, a foreign key denum to project. So this is for the controls relationship between department and project. So each department may control some number of projects. So project is on the end side of that relationship. So therefore we add this field to project, and this will point to the primary key of department. Any questions about this? There's a question. So null values may be presented. So yeah, so your tables can have some null values at this point. Okay, so this is just a general mapping algorithm that gives you some set of relations or tables from your ER model. It doesn't yet give you like a particularly good set of tables, right? So that's where normalization comes into play. We will talk about that in a later lecture. But for now, yes, some of these foreign keys can be null values. Okay, so unless, of course, the ER model specified that this is a total participation, then you don't have any null values for that corresponding field. Okay, so now let's move on to the fifth step. So in step 5, we have so we're basically left with still mapping binary relationships, but now we are left with the M2N ones, the many-to-many ones. And here we are stuck with the cross-reference approach. So now we can't use the foreign key approach anymore. So therefore we create a new relation R. And now we include the primary keys of the participating entity types as foreign key attributes in R. Okay, so and also the difference now is that their combination forms the new primary key of the relation. Okay, one relation that we're talking about. Also, we need to include any simple attribute that we may have of the M2N relationship type. All right, so if you think about it, this is so the main difference of this step, the way we use the cross-reference approach here in this step compared to the one-to-one relationship types is that now the combination of the primary keys of these foreign keys forms the new primary key. Okay. So now we do need to use the combination because this is the many-to-many relationship. So there might be the same relationship or rather the same entity showing up multiple times. And just to make this a bit clearer, here's a picture of how this works. So on the left here, we have some entity EA, and here we have an entity EB, and they're connected by this M2N relationship R, which has an attribute A. And in this step, we map this to a new relation R, this table here. And now this relation R gets the two primary keys as foreign keys, right? So it gets the one of EA and the one of EB. So those are my new primary key now together. And it also gets the attribute A of this relationship. So coming back to the company database, so how do we do this for the works on relationship? So that was between so between employee and project, right? So each employee might work on multiple projects, and each project might have multiple employees working on it. So now you can see that we include the employee social security number and the project number. So we have two foreign keys. They're pointing to the corresponding primary keys here. And we have these as our joint primary key of this relation works on. And we also include the hours, which was an attribute for this relation. Okay, so any questions about this? No, good. Okay, so let me just, actually forgot to run the second part of the poll before, so let me do that now. All right, so let's end the poll. Okay, so okay, so there seems to be an almost equal distribution of opinion here. So let's look at the first one. So dependent has a total participation constraint, meaning a double line from dependent to employee. So that's still true, right? So usually the company won't keep track of dependents, even if they have a unique social security number, if they're not in any relationship to some employee. So we still have total participation for dependents. And therefore, the first one is correct. The second one is not. Now, the third one here, so employee has a total participation constraint. So some of you seem to think that. So actually, it's still only a partial participation constraint for employee, because we did make dependent a strong entity, but that does not mean that now every employee suddenly needs to have a dependent. Okay, somebody might not have any dependent, and they still need to be part of the employee database. So in this case, the fourth answer was also correct. And the third one was, second and third one were incorrect. Okay. All right. Okay, so the step 6 here in this mapping algorithm, that is where we map the n-ary relationship types, right? So usually you won't have any higher order than 3, but you need to deal with the ones that you have. So for each n-ary relationship, we do the following. We create a new relation R, and we include the primary keys of the participating entity types as foreign keys. And we also include any simple attributes of the relationship as attributes of R. And then the primary key will be the combination of all the foreign keys. And now we come back to how we actually deal with the mapping of multi-valued attributes. So that's the last step in this process here. So for each multi-valued attribute A, we create a new relation R, and we include an attribute corresponding to A plus the primary key attribute K as a foreign key in R. Okay, so does that make sense? And of course, the primary key of this new relation R will now be the combination of A and K. Why do I need to make this the combination here? Isn't it sufficient to just make it K, which would be a primary key of of the entity type that I'm looking at? Well, the answer is very simple, right? So this was a multi-valued attribute. So for the same primary key value, you might have multiple entries, right? So you can't just make the primary key the primary key here. So you do need to use the combination of the attribute itself and the primary key, which is now a foreign key. And of course, if the multi-valued attribute is a composite attribute, then you're just going to include its simple components, as I mentioned before. So let's look at this example again in the company database. So we only have one multi-valued attribute there, namely the department location. So each department might have multiple locations, and therefore we need to create this relation department locations now, and we include as a foreign key the department number. So this points to the primary key of department. And now the actual attribute for which we're doing this is the department location, which we renamed to D location. Again, you don't need to rename it if you don't want to. And now the combination of these two will be a primary key. There's a question, which means we're combining two different attributes to one new attribute. So if you look at this, how we did this here, we actually didn't combine these two to make it to form a new attribute, right? So what we did was we created a new relation, meaning a new table that contains these two attributes. Okay. Because now if you look at this table here, this department locations table, so it might have some entries like this. So department 1 might have a location on Hong Kong, and department 1 might also have a location Singapore, and so on. Okay, so it might have, so this is how you basically model a a multi-valued attribute. Does that make it clear? As I said, so we are renaming attributes here. Okay. So let me go back to the company database. Not as simple to do on an iPad because you can't just jump back. Go step by step. But here we are. Okay, so department has an attribute locations, right? So that was a multi-valued attribute. And this attribute we now rename to D locations. Okay. And it also has this primary key number. And we used this and renamed it as department number. Right, we go back to the where we did that. Okay, so usually, so you have to use your own judgment whether you want to rename these attributes. In some cases, it does make sense to do it, right? In fact, it is necessary. So, for instance, when you look at the relationship supervision between employees, so you have to rename this foreign key that you add here, right? You can't have two attributes with the same name that are both called social security number. So there's another question. And just a reminder, if you send me a direct message, I might not see it because it might go to my iPad and I'm only looking at the messages on my PC here. So it's always good to send it to everyone, especially if you see that I'm not answering. So there's a question, why doesn't the location become multiple attributes? So the location was a multiple attribute, and that's why we mapped it to this relation department locations here, right? But now in department location, now you can see that we have tuples of the following form. Okay, so this is tuple 1, this is tuple 2, and so on. All right, so you no longer need to make this multi-valued attribute, right? So now this is just a simple attribute, which will have a simple value for each row where it occurs, right? So here it has the value Hong Kong, here it has the value Singapore, and so on. So no, department will actually not have, there's a question of whether department still have the attribute location. So you can see that we do not include it here in department in the relation that we got. And if you look back carefully to step 1, where we map these strong entities to relations, there it says that we only include the simple attributes and the simple fields of composite attributes, but it didn't say anything about these multi-valued attributes, right? So so far we ignored all multi-valued attributes, and only in this step 7 we resolve these by adding new relations for them. So there's a okay, so department location is still an attribute. So it is an attribute, but of department locations, but not of department itself. And there's a question, how about department name? So you could have also used the department name, but as you can see here, we only underlined department number. So this is our primary key, but we could have also made department name our primary key because both of them were identified as keys in the ER model. Right. So derived attributes, you can just, yeah, you're right that we didn't mention them here. So you can think of them as being simple attributes because you can compute them from other attributes. So you could do something similar when you add them here to your relation, to your relational schema. Okay, but We'll talk more about that when we look at SQL. Yes, that's right. So you might also sometimes add a new relation. Yeah, so you can use the different approaches, right? So if you don't want to use the foreign key approach, then you might want to, add a relation even for other relationships, not just the many-to-many ones. So in particular, there's one reason why I might want to do that. So if I want to avoid having many null values, so then maybe I want to create a separate relation that only, that basically contains the two primary keys of the participating entity types. And then I'm just going to, I'm not going to have any null values. I just have the tuples there in that relation instead. Okay, instead of having a foreign key involved there. That's right. Yes, that was the correct answer. And keep in mind that this was a very basic way to obtain relations from an R model. So at this point, the relations that you get are not really that great to actually be used in a real database, right? So you still need to perform some additional steps to make them better. Okay, so we are actually already out of time. So if there are any more questions, I will still be online for a few minutes in the chat. Otherwise, I'll see some of you in the tutorial on Tuesday and the rest of you in the lecture next week. Thanks. Yeah, so the university has sent out another announcement. So yeah, we're going to keep the tutorial online for now. As I said, I will send out an announcement once that changes. Oh, and some of you had some troubles joining the tutorials. So none of the tutorials are password protected. So you should be able to join them as long as you logged into Zoom with your city UID. All right, then I'll see you next week. Have a good evening.